Let's take a look at applying the chain rule to find the derivative of the function f of x equals the quantity 2x plus 3 raised to the 7th power. First, we're going to use the Lagrange differentiation notation, that is, using these prime indicators for derivatives. So if we're going to do that, we need to first identify what the outside function is, or what the main function is, and then identify what the argument of that function is. So as we look at this function, hopefully the first thing you notice is this function indicates we have something being raised to the 7th power. So we could think of the overarching function being f of x equals x to the 7th power, where then the argument or the function at which f is being evaluated would be what is inside that 7th power, or 2x plus 3. So in doing that, then we can compose these functions to make sure we are interpreting correctly. So f of g of x, if I replace every instance of x within the f function with the g function, do I get what I started with? So my f function was x to the 7th power, so I'm going to have something to the 7th power, and then I'm going to replace every instance of x with the g of x function. G of x function is 2x plus 3, and yes, that does match the original function we were asked to find the derivative of. So we are convinced that using f of x equal to x to the 7th power and g of x being 2x plus 3 is a reasonable thing to do. So here we go. So we want to find the derivative of f of g of x. And for that, we need, first of all, f prime of x. Well, recall that we said f of x was x to the 7th in this composition. So f prime of x should be 7 times x to the 6th by the power rule. So we want the first part of applying this chain rule is to take f prime of x and replace every instance of x with g of x. So we're going to start with 7x to the 6th, but recall that we're replacing x with g of x. So 7 something to the 6th, and that something is my g of x. So that's 2x plus 3. Continuing on with our chain rule, we now need g prime of x. So we claimed that we could use g of x as 2x plus 3. So g prime of x will be the derivative of that. So derivative of 2x is 2 times 1, using both the constant multiple rule and the power rule, plus 0 using the constant rule, or just simply 2. So we have 7 times the quantity 2x plus 3 raised to the 6th power times our g prime of x, which is 2. So then we could take our 7 here and our 2 and go ahead and multiply those together. Since this is, we have multiplication 7 times something to the 6th power times 2, and multiplication is commutative and dissociative. So 14 times 2x plus 3 to the 6th power would be our derivative using the Lagrange notation. Now there is a second way that we could think about applying the chain rule, and this is based on Leibniz notation and can be particularly useful when studying applications of derivatives such as related rates. So let's take a look at this notation. So in this notation, we're looking for the change in y with respect to x. So in this interpretation, we're going to decompose our function a little differently. We're going to start by calling our outer function y, and instead of saying this is x to the 7th like we did with the Lagrange notation, we're going to introduce a new variable u, and we're going to say that y is equal to u to the 7th. So this expression of y equals u to the 7th captures the behavior of that outward or outer function. And then we're going to let u equal the argument of that function. And in this case, that would be the 2x plus 3. So now, when we use this strategy, we need to know what dy du is. So what is the derivative of y with respect to u? Well, y is equal to u to the 7th, so dy du would be 7u to the 6th, because y was equal to u to the 7th. And then we need to know what du dx is. So du dx. Du dx, or the derivative of u with respect to x, is going to be 2. Or 2 times 1 plus 0 if we're paying attention to all of the rules, which simplifies to 2. And that's because u, we said, was 2x plus 3. So now our dy dx is equal to the product of those two derivatives. So 7u to the 6th times 2 for our du dx. Now there's one last thing that we should do, and notice that this is a derivative with respect to x, which means that in my derivative, my independent variable should be x rather than u. So what I need to do is I need to come up and grab what my u is and replace it in my derivative. And while we're doing that, I'll go ahead and multiply the 2 and the 7. So dy dx is equal to 14 times 2x plus 3 to the 6th power. So notice that both of these strategies incorporate the same ideas, the difference being in how we communicate or notate those changes. And as I mentioned, when you study related rates, this Leibniz notation is often much more powerful in helping solve problems such as those. I hope this helps.